We have now the third lecture and the second exercise. It is up here, and what it is about is here. You can play with that if you like during the break. We start from some position with this steel, and we have two magnets which are here, and it might go to one of them or just get in the middle, being attracted by none of them. And you are going to simulate then the trajectory of this lump in the second exercise. Those who were present on Thursday got already a very good introduction by Radar on using, on doing the programming of the ODEs, using Euler's method and ODE 45. ODE 45 is a built-in tool in MATLAB. For those who were not present, Radar promised to put that on the homepage, so you'll find it there. And today we'll go into a theory of that. That will be a repetition of Calculus 4, Mathe 4, regarding the numerical solution of ODEs. Before doing that, I would like to have a little recap on what we discussed last time, that is the sources of error. So that is our chapter 3. We discuss it here particularly for CFD, but what we discuss here would also be valid for other computational disciplines. And we looked at the finite difference method, and which we also had in exercise 1, and there we identified the truncation error. As an example, we want to look at the central difference as a repetition, which we also treated in the exercise 1. In the central difference, we assume now for checking the accuracy that we have some given function u of x. In the example, it was the tangent of x, but it could be anything else. And then we make the approximation that we say we try to approximate this derivative at a point x by computing the function at u of x plus h, subtracting u of x minus h, and divide by h. Actually by 2h, that's important here. So, and then we want to analyze that. The tool to do that is Taylor expansion. So we do a Taylor expansion of u of x plus h around x. So then we get the following. For u of x, h, we get u of x plus h. Now, if I write it explicitly, it would be, I write here partial derivatives. Actually, it would be a normal derivative, but we think already further on when we have dependence on x, y, or maybe t. So that will be then u of first derivative, and then we will have h squared half, second derivative, and we will have h to the power 3 divided by 3 faculty, which is 6, times the third derivative u of x with x to the power 3. And higher order terms. So that will be the representation of u of x plus h. So that's a Taylor expansion for that. Now we do just a similar thing for u of x minus h. So then we get u of x, now we do this, and then the rule says now we have to take the minus here. And then we have minus du of x dx, and then we have minus h squared, which is h squared divided by 2, the second derivative of u with respect to x. And now we have minus h to the power 3, so therefore we get this here with a minus, divided still by 3 faculty is 6, and the third derivative. And higher order terms. It depends on the order that you're investigating, how far you go with the Taylor expansion. So that is then this, and we have to divide by 2h. now we see a lot will disappear in this here. And what disappears immediately is the u of x. And then we see also that the even derivatives, for example, this one here, we have here a minus, that disappears, and it would also apply if we had taken h to the power 4. All even derivatives will disappear. And what is left is h du dx minus minus is plus, so 2h du dx in the numerator. Divided by 2h, that gives then d of x dx. So that is with this, and that is what we want to approximate. But now we get an additional term, and actually many more. We just write the leading term. That is this one here. And here we have minus, minus, so we get this twice. So we get 2 times this term divided by 2h. So altogether we get then plus h to the power 2 divided by 6 times the third derivative u of x dx to the power 3 plus higher order terms. And then we can see that this term that we have here, actually it is the terms because we have not written the higher ones, that is the truncation error. That is the truncation error of the central difference, which we denoted by TE at x depending on the grid spacing h. So then you see that we get, in this case, a truncation error, which is of second order. That is determined by the power here. So we can then say that the central difference, say u of x plus h minus u of x minus h divided by 2 delta x is equal to the first derivative of u with respect to x plus truncation error, which is of order h squared. And the meaning was that we can estimate this truncation error by some constant times h squared. And the constant that, if we would do it really exactly, it would be actually the third derivative at some point between x and x plus h. But the important thing is the h dependence. Because there we can see when we refine the grid, when we, for example, take h half, then also this error term will then have h half to the power 2. So we'll have h to the power 2 divided by 4. So the error that we had with h will be a quarter, a fourth of that what we have with h. So the error goes down more rapidly than with the first order method. For first order method, the error will only be halved. So that is then an example of a second order method. So then we have an idea of the truncation error. Now the next point that we looked at, that was the rounding error. And for the rounding error, let's see, can get that up here. Take that away. Yes, it is this one. Try to get that a little bit bigger. So that is taken from a home page from the Max Planck Gesellschaft in Berlin of computational genetics. So they have apparently also used on knowledge of single and double precision. It seems that you have not seen that before. Who has seen that before? Single precision, double precision. Okay, so I think this is very important to know in for the basics of doing numerics. It's interesting on its own for computer science, of course. If we want to represent a number on a computer, we have to represent it as a so-called floating point. And that consists, we do have a binary, by the way, we have only 1 or 0, binary digits on the computer. And then we represent the sign, which can be plus or minus. And for single precision, we have for the exponent 8 bits. And for the so-called fraction, which contains the digits of our number, and that will be the first ones, we have 23 bits. It is a convention that it is normalized. So we have always, when we think of bits, we have always a 1 in front. So that gives us then a fraction, which the 1 we don't need to store. But we have in effect 24 then. And then we can represent numbers with that up to a certain limit. But there, and for example, here we have some examples. I like this one, the 6.5. So in that you would represent in a binary form as 1.101 times 2 to the power 2. And that is also a trick in the computer. The exponent is represented with respect to 127. So, and in that case, then you would represent this number on the computer. It is plus with a 0, and here we have to represent then the 129, which is then minus 127, the 2 that we want. And then we have here the 1 that we don't need to store because of normalization. We need only to store the 101 here. So then you can figure out, using powers of 2, that this is true. So that is single precision. For double precision, we have more. By the way, this altogether gives 32 bits. One number, one word is 32 bits in single precision. In double precision, it is just the double. So here we have double, and then we have again 1 bit for the sign, but now we have 11 for the exponent. And we have 52 bits now for the fraction, for all the digits of the number. And that gives us, of course, much better possibilities to represent numbers with more and more digits. There is one number that Radar also showed in the lesson on Tuesday. I showed how to compute that, which is important. That is machine epsilon. And that gives us a clue of the precision of the computer that we can expect. And the precision is important because if we represent a number on the computer, we make a rounding error. So that is now the number 2. So a floating point number x has the relative error, that is due to rounding, that is I call it epsilon round divided by x. So we take the absolute value, and then the rounding error, that is meant floating of x. That is the number on the computer. So we call that floating of x. That's the floating point representation of the number x on the computer in the way that we just discussed. And that is minus x, that would be the rounding error, divided by x, and we take the absolute value. And the important thing here to note is that this is smaller equal machine epsilon. And this number is then different depending on the precision we have on the computer. And we have the standards given by IEEE, the Institute of Electronic and Electrical Engineers. And this standard is also used in MATLAB. MATLAB has the standard IEEE double precision. So if you don't tell anything else, you get double precision. But if you tell it, as indicated in the first exercise, if you say single of something, you get single precision. So the standard again is IEEE. Double precision. The machine epsilon, you can show that, is 2 to the power minus the number of digits you have for the fraction. In our case, it's 52 plus 1 for the normalization, so it's 53. And if you compute that, that is around 10 to the minus 16. So that is then double precision. For IEEE single precision, we have the machine epsilon to be then, according to the number of bits for the fraction then, that was 24, including the one for the normalization. And that is around 10 to the minus 7. And in MATLAB, you can get this machine epsilon by using EPS. EPS is actually 2 times machine epsilon. So it's a double. So that is very important. As you saw in the exercise 1, it makes really a difference if you use single or double precision when the rounding error shows up. And it is important for you, therefore we did this exercise, to be aware of this problem with the rounding error. Just try to get this a little more stationary here. So usually you are in the range for h where you don't see it. But sometimes you can run into this problem. And we did that when we computed aeroacoustics. So my PhD student at the time, Jan Zesten, got very strange results, and he found out himself that it was this rounding error. So he, at the time, it was computed by single precision, but even if you would have double precision, it would have affected the results in some way. So then the solution was to compute the problem not computing pressure, like here, 100,000 Pascal, and having very, very small pressure changes from acoustics, it's less than 1 Pascal, but just computing everything or formulating everything in terms of a reference. So we then compute it not with the pressure, but with the reference pressure, the pressure related to, for example, ambient pressure. And then the problem was gone. So that is then something to remember when you do computations, that you should be aware of when you do grid refinement and you get strange results. There can be other reasons, but one reason might be that you run in rounding error. So let us look at other errors. These two errors you have now seen, and they are present at all the time, but as you noted in exercise 1, for the larger h, it was the rounding error that was dominating, and you could see how the error was decreasing either with first or second order, or even fourth order. And then when h gets smaller, the rounding error took over. You can actually estimate both and then find out where this minimum occurs. Let's look at further sources of error. And the third one is iteration error. So that is an error if an iterative process that you have in your computation has not sufficiently converged. As an example, we can consider if you want to have a nonlinear system, so we want to solve the linear system, say f of x equal to 0, so we assume that this is nonlinear by Newton's method. So where the f of x is a nonlinear system. So then you know that you have to use an iterative method, and you have done that in mathematics 4 or any other subject. You know you do have to do some iterations, and you have to stop the iterations at some point. And then you might not have converged long enough, so that you still have a too big error. So, if Newton's method has not converged, for iteration k, then that means that f of x is not 0. And this is the iterative solution. I denote that by a superscript k. So the xk is the kth iteration. And then the epsilon, call it eta for iteration, would then be the difference between the iterative solution at iteration k minus the exact root of this nonlinear system. That would be then the iteration error. So then, usually we don't know this x, but what we know is the previous one, or the next one, say xk plus 1. So then we can check whether this difference is small enough. And if you want to do it really well, you would do that such that the difference, then if it's a system, you would have to take a norm, that is, say, in the range of machine epsilon. You cannot do better than machine epsilon. So if you get it down like that, then you can say that's the best you can do. But if not, then you have an error due to not converged iteration. Next class of error is the discretization error. That is the error of the discrete solution that as U discrete, like that, discrete. And we assume that this is now a discrete solution of a PDE model. case it would be a PDE model of some fluid flow problem. But we assume that the PDE model has an exact solution that we know, which we call model U model. Then we can identify then this discretization error as epsilon discrete is then equal to the discrete solution that we have computed with our numerical method by discretizing the PDE model with respect, then we take the difference with respect to the exact solution of the PDE model. So then we check how well does our discrete solution approximate the exact solution. That we can check with that. And that is what we will do mostly here when we discuss the numerical solution of model equations. Because that is the big advantage. We know exact solutions. So then we can do that. Then we can check our numerical methods for that. And this is one of the important tasks to do in CFD. It has a name, it is called verification. I'll just write it. So checking the discretization error, epsilon discrete, that is done by comparing the discrete solution with the exact analytical solution. So that is a solution that we can write down as a mathematical formula. That process is called verification. So what we do is we check whether the mathematical model is correctly implemented. Checking whether U discrete is computed right, we can say it shortly. And that is the thing that is always the first requirement. If we develop any program in CFD, also in other disciplines, but here we discuss CFD, that's the first thing to check, whether we have done this correct. Because if we have done an error here, then everything is unreliable. If we have a mathematical model that we believe is describing the physical problem well, we want to solve this correctly. And that is done here. That is the first step. When we have done that, then we can really attack a true problem of fluid physics, try to solve that. And then we face another problem, that our model might be wrong. So that we have a modeling error. That can only be checked when we have first done the verification, that we can really rely on our numerical solution, that solves the PDE model correctly. So this error is then called the modeling error. That is the error of the mathematical model discussed previously, described by PDE, with respect to the, I call it here, the real flow physics. So that is really that's what we want to describe, that we can call the U real. So that means that the modeling error is then the difference of the model, solution of the mathematical model, minus the solution that we have in the real flow physics. So we are checking the modeling error by comparing computed model results, because we can hardly do it analytically. So it would be the U discrete that we discussed before, but we assume, and when we have done the verification, we can trust in that that is really approximating the mathematical model solution well. So this is assured by the verification step. So then we compare these computed model results with experimental results. And for the experimental results, we assume, and that has to be verified by our experimental colleagues, that is modeling or describing, not modeling, but describing the real flow physics properly. We go in the wind tunnel, do measurements of the pressure there. We must be sure that the measurement technique is working correctly, must be checked, must be calibrated and so on. But if that is true, then we have really something that we can rely on. And this process is called validation. And that is essential. So here we are checking whether we are solving the right model. So then you can see the two things. Verification, checking whether U discrete, the discrete solution is computed right. And here we are checking whether we are solving the right model, whether we are computing the right model. So we are focusing here on the model. So then you usually see graphs where you have numerical results, experimental results. You see then estimate the difference, and you see that the difference is small, and it's okay. If not, then you have to choose another model. So these processes of verification and validation are essential in CFD. Even if you have a CFD tool, you should, well, they should have done the verification, but it doesn't hurt to do it also, to check some things there. And then you want to solve a problem, try to get a good experiment and compute that and check it for that. It can be a very simple experiment, but that is usually very helpful to see whether you are using the right model or not. And that is essentially central if you're doing flow computations with turbulent flow, because turbulence is still very nasty and very difficult. So therefore also you, Jürgen, are dealing with that in your PhD project. So therefore, we still have to use a lot of models for that. We cannot afford to resolve everything what you try by using DNS, but that cannot be done for most industrial applications because the scales are too big and would cause too many grid points that we cannot represent on any computer today or tomorrow. Okay, so that gives you some idea that you should be aware of when doing CFD, which sources of error you might have, and that these processes of verification and validation are essential. So the next point will be a review of numerical solution of ordinary differential equations. That is supposed to be a recap of what we have done and seen, computed, doing exercise on in mathematics 4, calculus 4. I'll use this book as a reference. In the break you can have a look at it. That's the book by Michael Heath, Scientific Computing, an Introductory Survey. So that contains really the basics of numerics and also of numerical methods for ODEs. If you want to go into detail, then I have here a book that really contains a lot. There are actually 2 volumes. I have just brought with me volume 1, and it is by Heira Nørset Vanna. Sivert Nørset is here from NTNU, so there's a very good math group on numerical methods for ODEs here at NTNU. And the other authors, Ernst Heira and Gerhard Vanna, they are from the University of Geneva in Switzerland. They have 2 volumes and there is a newer edition. This is the old edition. So these are very useful references. We do it because it is interesting in its own, as we see in exercise 2, as you will see, that is simulating this process here. And it is important for the time discretization of partial differential equations. So then, that will be then our chapter 4. Numerical solution of ODEs, ordinary differential equations. And we shall focus here on initial value problems. We have also boundary value problems, but we shall not consider them here. We look at ODEs in the following form. We have y prime is equal to a right-hand side. That's a function of our marching variable, which will be in our case time, and the unknown y itself. If we would write that explicitly, it would mean that we have the first derivative of y with respect to time is equal to some given function f depending on t and the unknown function y at time t. And the y and also the f can be scalars, but in our case they are usually vectors. In the exercise 2 we have a second order ODE. We formulate that as a first order ODE, as Reda showed on Tuesday. By the way, you'll find the material on the homepage. And then we have a first order system. And then we have this formulation. And we do that with an initial condition by IC. IC shall stand for initial condition, which is in 1b that we have at our starting time t0, which usually is actually 0 itself, that we have given there our unknown y0. That is the initial condition. So the y0 then is given. So that is the framework that we are dealing with when we consider initial value problems for ODEs. The first method that you certainly remember, I hope, is Euler's method. This is also called explicit or forward Euler method. Explicit Euler method or forward Euler method. So in here we assume that yn, that is now the notation. You can also have different indices there. Some call it k, I call it n, yn. So we assume yn, and that is the solution, the numerical solution at time level n, which means that it is at Tn, the time instant Tn, that is known. So if we are starting, it would be the y0, or initial condition. When we have already computed n steps, then that will be the solution that we have just computed, the yn. So then we want, starting from that solution, we want to compute the next. So we have y here, say we have Tn here, then we know, say the yn, we assume that we know that. But what we also know in yn is the slope of the solution. So the slope at Tn, that is y prime of Tn. How do we know that? Well, simply by using the ODE. Because we know f, we know t is at Tn, and we know the solution there, yn, so we can compute that. So it means that is f of Tn yn. So we can compute that. And that is used. So suppose we have the exact solution would be, we don't know the exact solution, let's say too large. Maybe it would be something like that. Still going too large. But what we know is the slope. So if we know the slope, we can use that. So that is the slope here. That we can use. And that is then what we do. We determine, say, the grid spacing, that would be then the Hn, going from Tn to Tn plus 1, we determine that, and then we can use this slope to get from here to Tn plus 1. So we use this slope here to get to the solution here, which will be then our yn plus 1. So that means we compute then the solution in the explicit Euler method or in Euler's method by starting by yn and computing this difference here. So here we have so this is hn that we have here, this distance here, and this difference here we can compute by multiplying the slope by this length here. Then we get this, because the slope is the change in y with respect to the change in t. Then we do it like that, hn times the slope. The slope we have just said is f of tn yn. So then we have already Euler's method. So the recipe is starting from the solution that we have at time level n, using the slope there, and just using that to get from the time level n to the time level n plus 1. Okay, so we stop here, take a 15 minutes break.